all, we're going to talk about what we do with these microscopes, right? So, microscopy is a really, really old field. People have ground lenses for a very long time. First time they ground lenses that we know of were found in the desert, and they were reading glasses. As we all know, after 35, we start to have problems. And yeah, I discovered this myself, and I'm so grateful to optics, even more so after having made this discovery. But microscopes are also quite old, and telescopes as well. And there is really a limit to what we can do with them, though. And this was discovered in the 1800s by Ernst Abbe in East Germany, Jena, which was not really East Germany then, right? It was just Germany already. And he discovered that there was this limit of the resolution that we can get when we image with visible light. And my PhD advisor, Mats Gustafsson, who dragged me to California from Sweden, as he himself had made that journey, did beautiful work in this. Okay, is that better?
Yes.
Yes, I can also just stand over there and project more, but this is good now?
Yes.
Okay, we got it. I may want to, can you make this a little bit higher so I don't like slouch when I talk? Okay, so what we see here is a cell. It's a mitochondria that's stained in this cell. And we see little structures inside them, and those structures are smaller than this resolution limit. And this cell is imaged in 3D, and it's alive. And this is what we can do today, and the only way we can do that is by building these custom microscope systems that have unique capability. And the reason I came to Santa Cruz is that we have here a phenomenal biology department and a phenomenal microscopy facility manager who wants to build here what we have built already, for example, at Genelia, where I have a microscope commission. So with that support, I've been here for 1 year now, and the first system is almost up and running. We also got $1 million from the NIH to build another system in the imaging facility. So it's been a fantastic year here, and I've gotten incredible support from colleagues and mentoring and help. So let's get into, here's my lab. I also was lucky enough to recruit 2 fantastic PhD students and a bunch of undergraduate students. We also have a lot of fun together. We do lab retreats where we go surfing, and this is where I finally get to hear from the students what they actually want to work on and how they're feeling about things. So I think we got the right thing going. But one of the images is from my lab here, which is filled with equations, optical tables, and systems being built. Here's the nanofabrication facility at our sister university in Santa Barbara, where I just drove up from, helping these guys doing some nanofabrication of optical devices in order to come and hang out with you all. And here's my recruitment slide. If you have, younger relatives who are talented, please come join me and build microscopes. This is what we want to look at. One of the things, it's a little steel wire model of DNA, right? Because this is one of those things that we can't see. Our DNA is so small. This is a 10 nanometer scale bar right here. This we cannot see with visible light yet, and that's one of the challenges that I want to address here. So what is microscopy? Those of us who work in microscopy tend to say that microscopy is an unfortunate series of compromises. You pay for everything you want. You want the live imaging. You want to image with visible light. Visible light has limited resolution. You want to image a cell. The cell is 3-dimensional. You want to image an animal. The animal is 3-dimensional. Photography, microscopy, everything is 2-dimensional, right? You have a certain amount of photons you can get out of your sample. You have a certain amount of speed you can image at. Biology moves. This is, from the last 10 years that I've been working in this field, has had a 10-fold improvement. And we can now do things that when I was in grad school, we couldn't do yet. And I built systems knowing that technology and electronics and sensor technology has to develop for me to be able to employ the methods I'm developing, and they have, and I was lucky. Super resolution microscopy, very, very important to us to go beyond this diffraction limit of resolution, but then you have all these complicated systems that you have to make user-friendly. And then we come to the really problem that I solved during my PhD, which is fast imaging in 3D. So everybody is familiar here, we're in California, with the F64 groups. We're all old enough in this room that we don't only have our cell phone camera, right? We know how real photography cameras work. My lab is learning that. I bought professional cameras to everyone in my lab so that they would learn what an aperture is and what depth of focus is. Yeah, you're laughing, but this is still important today. So this is the F64 group, F64 of course being the F number of the camera that Ansel Adams, Imogen Cunningham, all of our favorite photographers, Edward Weston, used when they, as we do, went up in the high Sierra or out in the desert and wanted to image the grand scenery and discovered that the little cholla cactus here is completely out of focus when I focus at it. Now we have a ringing going on here. Okay. When I focus also at the mountains. But here they solved this, right? They have the stones at the shore right next to us in focus, and they have the mountains all the way back in focus, and we all know how they did that, right? They put a pinhole aperture almost, a 2 millimeter aperture, to get this incredible depth of focus. It's ringing here, I hope it's not ringing there. Okay, it's sounding metallic in my ears, maybe it's just ringing. Yeah, so that's what you do, and this is 3D information in a way, right? You have a 3-dimensional world here, and everything you can see it. However, you have no idea where anything is unless you use your prior information and you realize that this stone has to be right next to me in the mountain very far away. So in microscopy, we solved this the other way. So here I'm in Central Park. I took a day off my postdoc at Rockefeller to go and photograph in the park here with a very large aperture, which means that I have a very small depth of focus. And the cherry blossoms here are in focus in different planes. And this is what we do in biology, inside the cell, except in the cell, things are transparent almost. So we can even see through them. And now we have 3D information, and we can say where everything is, right? So that's how we do it. So here we have an imaging system that in a little bit you will understand completely, which does the marvelous trick of taking all of these photos at the same time. Because imagine that here you cannot really see it so much, but in biology when things start to move, if you're imaging animals or living systems, things move between the time I take those 2 images, right? I mean, even if I have a very fast piezoelectric stage that says suck, 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 going through the sample, this is not infinitely fast, and we are looking at things that move very, very quickly. We're often limited by camera readout speed, actually, even less so today, though. When I started out, we had 35 frames per second. Now we have over 100. I can buy a consumer camera that runs at 140 frames per second that still has pretty good, decent photon count efficiency. So here's the system, right? And what do we use? We use diffractive optics. So nobody uses diffractive optics. We all know that we use refraction, right? We have lenses, we focus light in lenses. We also use reflection. We have astronomers here, they use mirrors, right? Curved mirrors, reflection. Diffraction, now we get into the wave nature of light. This is a break at pleasure point, and I'm just reminding everybody that we can think about light as water. Because it turns out, and I'm going to do a little demonstration now, if I'm a light wave, and I'm coming just like water. And if this is an object, a very small object, and I'm a light wave, and I come at this, I refract and I ripple just like water. So if it was water flowing here, flowing at the edges of the chair, the water would actually spread out in waves, and so does light, right? So if we can make shapes very specific in glass that either block light completely, so that there's blocked and transmission and blocked and transmission, at every edge here, the light is going to ripple and it's going to spread. So that you will believe me, because I know that there are people here who are not engineers, I brought some diffractive optics with me that I've made myself, and I'm going to send them around in the audience. And so like I said, you can do this by blocking light, transmitting light, but you can also do it by putting a base step in the glass. So if I have a glass surface, and I put little steps in different shapes, I can start to ripple the light. And using computer models, I can model exactly how this light is going to ripple. And I can use these kind of elements to multiplex beam, to phase shift beams, and to do all kinds of things. And because the element is completely transparent, I don't lose photons, right? Because we're looking at single molecules a lot of the time. We've labeled some living specimen with fluorescent proteins that we shine light on and excite, and they shine light back, and those photons are sacred, right? We don't want to take them away. So I will send this little guy around in the audience. This is a phase-only diffractive grating. It's made of UV-grade fused silica glass, and the center surface here has a pattern on it that you can't see, but you can see effects of that. So Why in the world do I want to do these 25 dots? I will explain that, but here you just see the potential of my optic to multiplex the beam. So I'm going to send this around. Don't point this in each other's eyes, or your own, and here we go. So I'm going to send separately around the mask that this was made of. Don't put the laser pointer in this because it has chrome on it, and this is all nanofabrication. So in case anyone is interested in deep UV lithography, you can take a look at this little guy too. So that's the mask that this was made of. So that was multiplexing of light, and the way diffraction works is also, it depends on how fine this pattern is that we put in, what angle we get out. And the way that works is the finer, the squeezier the pattern, the more deflected the beam comes. So if I'm a beam now and I'm a light wave, and I'm coming through this big aperture, I'm deflected less. And if I'm a big light wave and I'm coming from a bigger, so the bigger one affects me less. So it's easier to squeeze the light, kind of. And if I have a fine pattern, I'm deflected more. So I can control the angle. So those points there, they're beams, they're rays. The angle at which they come out, I control by controlling the pattern. So here we have a grating, we have a lens, we have beams coming out of the grating, just like that one. And that is going to multiplex our image. And I'm missing a slide here. And hold on, we'll go forward to it. So this is what's going to, this is terrible. I took out the slide. So we'll have to go through it like this. So we have a lens, we have a grating, that particular optic that's going around in the room right now. If it has a periodic grating, it's going to exit the element like this, at the same angle everywhere. And if I now have a distortion in that period pattern, so here, this one is not very strong. Up here I have a tight beam coming out, a tight grating and a very high deflection angle. Down here I have a much sparser period of my little pattern and a smaller angle. So what happens now when we put an image through this is the image is refocused. So here's the focal plane of the imaging system, a lens. This is Fourier space right here. This is the back focal plane of that lens. This is where we place the optic, that particular optic that's going around. And now it's going to send these beams in different directions. And because of this design of the pattern that I've made, this is going to be refocused. And then we have an order that goes down. And the order that goes down is defocused in the opposite direction. So what have I done now? I have done that magic trick of taking multiple focal planes at the same time, so like the stones and the lake and the mountain in the background. I put them through the imaging system and I put them on my camera at different positions with different focus. And here is a cell. It has a nuclear pore complex labeled. I don't know how well you see it here, but here's the top of the cell with the little nuclear pores everywhere. Here's the middle of the cell where these little pores are like a pearl necklace around it. And here's the bottom of the cell on the cover slip. So that is what diffractive optics can do for us. And to design that, we designed a grating function. I use MATLAB because I don't know all these modern languages. I just know BASIC and MATLAB. And you have a guess and you say what's your target function. So here our target function was 25 spots for that grating. What I'm showing here is 9 spots, and that's just how many images you get out, right? My students also make pictures of little guitars as their target function, so when you put the laser beam through the optic, you get an image of a guitar on the wall, and sports cars and whatnot. So you can use this to display any type of image that you want. Here is another design which is absolutely superior. Like I said, we want to have every photon captured, and as you see when you shine the light through that little optic there, you have not only those 25 images that you want, but you have higher orders. So the energy that goes in those orders is about 33%, and 67% go into the orders you want. If we make this beautiful pattern on the right, which has 8 layers, so this is all glass, this is layers in glass, all the light is transmitted, then we can get 89% photon count efficiency. And I thought that was good enough to spend a large portion of my life learning how to make diffractive optics, and I hope that was worth it. So again, this is what happens if we just have a periodic pattern that multiplexes into 9, we get the identical image of the cell. Now we distort the pattern and we get that focal series. And we distort it according to a function to calculate the proper focus shift in each plane. I use the Abbott sign condition to see what out of focus phase error I have in each plane, which means that this is aberration-free refocusing. Because you could imagine doing this with a beam splitter and just refocus everything, but then you get spherical aberration, and you can maybe do this over 2 microns. After that, you are kind of dead in the water, and your point spread function looks like a rocket ship. But just using this formula, which I probably couldn't derive today, I did this 10 years ago, so I keep this piece of paper very, very close to my heart. And I use it every time. The MATLAB programs I still use, and then I publish. Of course, everything is online, so you can just go, if you want to make your little Ferrari car display grating, you just go to Figshare, which is one of the permanent online repositories, and you download the Pixel Flipper, and you tell the Pixel Flipper, this is the image I want to project, and the Pixel Flipper calculates maybe for a couple of days, because I'm not very good at programming, and then you get that, and then you can go to the open nanofabrication facility in UC Santa Barbara, and you can make these optics. We have a fantastic system here in the US. I spent 2 years at Cornell because I was in New York learning how to do this, and I had no clue when I came in how to make those little optical pieces. So now everybody knows what this is. This is the cover to the Dark Side of the Moon album by Pink Floyd. And this is chromatic dispersion. So what I just told you is working only because we are using a laser pointer. If you took that little grating and you looked out through the window and saw the surface, you would see a rainbow, right? It turns out that dispersion in diffraction is even more strong than the dispersion in prism. And this is why nobody uses this technique to image. So like I said, this is absolutely powerful. We can multiplex beams as we want. We can completely control the phase shift in each one of these beams. And nobody uses this except the military in some laser applications because of chromatic dispersion. So even with green light, when we image a green fluorophore like GFP in the cell, there's a green rainbow coming out. And I'm illustrating that here. It's absolutely terrible. There's a smear. It looks like the initial view of the Star Wars movie. If you image dots, there's smear out everywhere. So, of course, we had to solve this. And the way I first figured that we should solve this was we just put another grating in that will reverse the dispersion. So you can make a blazed grating where each little grating piece is like a prism, and that directs almost all of the light, actually 95% of the light, into the -1 diffraction order. And what we're doing is we're reversing the whole effect of what we did. When I thought about this, I thought I was really smart, and then I realized it actually does reverse everything we did. So everything ends up in the middle again, and then I had to design this beautiful prism, which is almost impossible to make, which we are not going to use anymore in future designs. We had a company that made it, Rocky Mountain Instruments, and it cost a lot of money and it took a lot of time, and it was only because we were at Genili at the time and had millions of dollars literally to spend that we could do that. So now I thought we're much smarter and better and faster design that we're currently implementing. But this really works. So like I said, now everybody understands this diagram here. Because we have a focal plane with multiple focal plane images. We have a lens, we have a diffractive grating, we have a chromatic correction module, and then we have a final lens that forms this image on camera. So there's instant 3D imaging. It really, really works. Here's some pictures from the nanofab where we made these optics. This is the multi-layer optic. You make that on a kind of looks like a CD wafer. Developing these techniques for using in these tools was not easy because everybody else is doing semiconductors. They're doing computer memories, they're doing image sensors, they're using things that are not transparent. So when I put my glass wafer in the tool says the tool is empty. So you have a lot of new challenges that we have solved. And Santa Barbara is a great place also to do this, although it was at Cornell I developed everything. Here's an example of yeast centromeres imaged in the microscope. This is the one that's at Geneva, so you can apply to go and use that one. They kept it there because they liked it, and they gave me money to duplicate it when I went to Rockefeller, because at first they had promised me that I could bring my microscope. So then I built more ones, and different ones. For example, what I did in my postdoc was to apply this in functional neuronal imaging, and I know that there's these two C. elegans people in here. So so they will know what we have here. We have a little nematode. It's a 1 millimeter size worm that eats fruit, so we probably ate some if we ate some fruit today. And they have almost more in rotting fruit, so maybe not. It has a set of neurons that are completely mapped. The wire diagram is mapped. We can with genetic tools, we can make all these neurons express fluorescent proteins, including fluorescent proteins that are only active when the neuron is active. We can also do optogenetics. I mean, I am a physicist, I came from physics, I came into biology and I said, whoa, it's okay, we have laser mind control. And I said, yeah, we have laser mind control. You can actually turn on neurons by shining light on them if you have genetically modified the organism first. But what we did here was not that, we just looked at function. So we have the green fluorescent protein, which is modified by calmodulin, so that it only fluoresces when there is calcium, which means when there is a burst of neural activity, it starts to shine green. So we can label all the neurons in the cell and image them in 3D with the system. We put the animal in this microfluidic chip. It lies in a little channel, its nose is sticking out, we can put smell past its nose, and we can see how this neural circuit reacts to that. Aversive, attractive odors. We can try to do memory, like when we drink too many gin and tonics, right? And after that we hate the smell of gin and tonic. How does this neural circuit change when this animal is poisoned, right? So this is how this ties in to me being in the electrical engineering department, because we study circuits, right? This is a circuit. How can we learn from biological circuits? Here's a little movie. It has a bunch of these neurons labeled, the key 2 sensory input neurons, and we can see them lighting up in response to function as we are putting almond smell on it. Of course, this is not optimal because this is only 3 planes. That's why I made the optic you have there, which is 25 planes. So that's the next step on this adventure, is to have 25, and we're going to do it with 25 cameras, because cameras are very expensive. When I designed this, and I built this the first time with 25 plane, it was useless because sensors were not big and fast enough. So astronomy has giant sensors, but they're very slow. You can buy a fast sensor, but they're not very sensitive. And today, I have in my lab 25 cameras in an array. They run at 140 frames per second. Each have a lens in front of them. And my students are just now in Santa Barbara making the optics that's going to display the images on each one of these cameras. And then those ones of your friends who want to do the fastest imaging that anybody's ever done in 3D, please send them to me, because we don't have the perfect sample yet. I think it might be the C. elegans embryo, and inside the embryo, look at the neural development from start to end with these functional dyes, maybe also in 2 colors. But we'll see what the biology project is going to be. I have no fear that this will be applied. I have an experience of creating new imaging systems, and you end up using them for so many more things than you thought that you would use them for. So I think this will be great. But this is the hard challenge right here. Can we image DNA, right? So we have very, very good chromatin organization groups here at the university. And I would personally like to see this. John Sadat at UCSF and Mats Gustafsson originally started the structural elimination imaging project, which was inspired by astronomy, in order to see the 2 strands, the sister strands of the chromatin in meiosis. And this is something that we could only see with EM before, right? So electron microscopy can resolve this, but light microscopy classically cannot. This is written in stone in East Germany, lambda over 2Na. Around half of the wavelength you image in, that is the wavelength you got, right? So electron microscopy, electrons have much, much smaller wavelengths. We can look at this. This is Ångström resolution, or angstrom as you say here. That's a 50 nanometer scale bar and 10 nanometer scale bar, and you're solving things within that, right? It's absolutely incredible. And what's the problem with this here?
Yeah.
It's dead. It's really, really dead. It's probably stained with plutonium, right? So we want to look with visible light, and this is structural elimination microscopy. This is what came out of John Sadat and Mats Gustafsson. This is from a microscope that I built in a little bit of different configuration. But you see a classical image on the left, and we haven't blurred this. Like, this is a really, really nice image, okay? And to the right, you see the 2 strands wrapping around each other, resolved by visible light, which means that we can start now to look at this in living specimens. And how do we do that? We do it by frequency mixing and aliasing and Moiré fringes. If you squint, you cannot see the stripes in those patterns, right? But even when you squint, you can see the mixed pattern. So what we're doing in structural elimination is we're putting stripes on our sample, and we're sliding those stripes across the sample. And the frequency mixing that happens And now I'm talking about spatial frequency. Biologists don't like this. I got yelled at this weekend by my boyfriend for that. It's like, what do you mean frequency? There's no frequency here, but we call that frequency, right? The pattern of the sample, and then you just slide this across it. Like here, like if you see these stripes, if they are too small to image, you can still see this stripe, right? So that's what the Moiré effect is. It's you put two patterns that are about the same size on top of each other, and you get a bigger pattern out that you can image. And then you use advanced computational methods to calculate back the image that was under it. So this is what the acquisition series looks for that little synaptonemal complex. This, by the way, is a mouse spermatocyte spread. You put all those stripes on, and then you calculate everything back again, and you resolve it. So that's structural elimination for you. Here is for those of you who are into Fourier space and optical transfer function. You can see that you both improve contrast and resolution. So this is a Dabby-stained cell nucleus. And that's what I want to do further now. So you have contrast improvement, you have resolution improvement, you can absolutely brilliant images. And here is back again to that one cell in 3D. There was something I didn't tell you when I showed you this the first time. Yes, the cell is alive, but it was several seconds to take each frame here, so they had to slow this cell down a lot. And what I want to do now is I want to do this very fast. So SIM, optical sectioning, resolution improvement, with nonlinear SIM, as an aside here, you actually get theoretically unlimited resolution, and here are 50 nanometer speeds resolved. This is also another tangent project that I want one of the students in my lab to pick up, because we can go much, much further than those 100 nanometers by using nonlinear effects. And anyone who will have a glass of wine with me after this can get to know that, but I'm not going to go through it now. So the problem that we have now is acquisition speed, right? This is Harold Edgerton, my favorite photographer from the Wimbledon P7. Yeah, things move very, very, very fast, and that's just 2D. So this is going very, very fast now with the pattern, and here we have one focal plane of 3D SIM data set. That means that if we want to take like a total 3D image of this, we need this many images. These are too many images, okay? So what do we do now? We take SIM and we take multifocus microscopy, and this is now very bright. We put them together, and then we only take those images. So all of the 3D technology with the diffractive optics, and then we put structural elimination on top of that, and then we'll get the fastest microscope in the world. And this is the only data set that's ever been taken by such a microscope. I built it in Stockholm 1.5 years ago, and I published a proof of concept article last summer on this, and that $1 million grant I talked about was to build one of these that actually is fully equipped for biological imaging in our imaging facility with Ben Abrams, our microscopy facility manager. He's fantastic. He's been a great support to me. He's given me a corner of his facility. So now I'm going to custom build this system at UC Santa Cruz, and we'll see what we can do with it, right? My dream is that we'll image chromatin with blue here, right? So that the SIM thing. And then we'll have two colors on top of that that are not structural elimination, that are just particle tracking, that are multi-focus, so that we can look at the associated proteins like polymerases or RNAs floating around in other colors. And I can't wait to see this data set, so I need to, this is way too bright anyway, that was just a reconstructed data set. Here's another reconstructed data set. Yeah, so now we're trying to build this. Here's the live data set that we tried to take in Stockholm. I built this on a commercial SIM system, so it was much too slow. And these are mitochondria, and you can see them moving during the acquisition sequence. So here we will address that. We will make our own structural elimination launch. We have bought a spatial light modulator that we put our laser light on to generate this pattern really, really, really fast. And here's Ben in his imaging facility, and a big thank you to the NIH. And with that, I'm going to open up for questions. We have a question.
Very interesting. I still work at X-ray spectroscopy. And it would be really nice if we could extend this several orders of magnitude in wavelengths down. So you could look at atoms moving in a crystal. I look at the big focal environment of every atom in a crystal, but it's average over a long time.
Yeah.
And what are the challenges to take smaller diffraction ratings so you can do this at soft X-rays or maybe potentially?
So what we're doing here, basically, this is interferometry. We're building an interferometer inside a living cell. You can build that inside crystal structures too. People have gone down to 4 nanometer resolution looking with visible light in crystals, which is, I mean, for you is nothing, right? I mean, these guys have 4 nanometers, come on. Yeah, I don't know how these ideas should be applied, but to look at that, we need to think both about this implementation, also what people did in astronomy with it. Because this is really frequency mixing, right? So can you get 2 frequencies to mix? Then you already, if you do that linearly, you have a 2 time.
They iodine already for medical purposes.
Yeah.
Above and below the iodine edge. And they mix them to look at blood vessels that have iodine in them.
Yeah.
All between that type of thing in specialized cases.
Yeah, to me, the key to super S is really non-linearities. Because, I mean, the diffraction limit, was that stupid? No, it was brilliant. Like, Amstaba really sat down and said, if I make these assumptions, so the assumptions are limited numerical aperture, uniform illumination, and linear processes. You break one of these, or you break all of those, and you break the limit, right? So physics still applies. It's like Newton's law. I have another argument the other weekend about, like, is that false? No, it's not false. It works under certain circumstances, and just because, you know, during certain circumstances that breaks down, and we, for example, have relativistic electrons in our electron microscopes, it doesn't mean that it's false. So the diffraction limit applies under certain assumptions, and then you think what those assumptions are, and you break them, and you go past it. The nonlinearity, to me, is the most powerful one.
Another question for Sara. Okay, one more.
Could you tell us maybe a few things that you are going to say about DNA that's new to this?
So me, not yet, no. I have not.
Found something that was not known before.
Lothar Schermele has a paper on that, and he really did biology on this, and he looked at nuclear organization with 2 different proteins. I am so uninterested in biology that I don't remember what it was, but I will be happy to give you that paper.
We're all very eager to use her scopes.
Yeah.
Quite ready.
Is there a photon limit such that the brightness that you can apply to these little features would block you? What is that limit in time for regular wavelengths?
This is the issue. Like, we put a lot of light on our sample. So everything we do is to minimize the amount of power we put and the amount of photons we get out. And in the end, we're Poisson noise limited. It's the shot noise, it's the photon shot noise that limits us. We have sensor noise, we can remove a lot of the sensor noise. Denoising data is becoming very, very important. I don't have a number of photons that you can get out of a certain sample, but what you do is you sit down on your image, and in C. elegans what you do is to say, well, eventually the fluorophores bleach, right? But by the time they bleach, you will usually already hurt the sample. So there we look at the development. Does the embryo hatch in 12 hours, or does it hatch in 15 hours? If it's 15 hours, you were bad. Like, this is not longer a healthy sample. So we always keep very, very big track, and that will be the limit of nonlinear SIM, right? So nonlinear SIM has theoretically unlimited resolution, but the practical limit is how many photons can you get above the noise floor.
Also, I assume that a lot of biological substances are sensitive to very blue light.
Yeah. So when you use UV, it's no good. Yeah. So even at 488, it's not good. And we're moving up in wavelength. However, the wavelength is longer, the resolution is less.
Yeah.
So we pay for that too. So 488 and 560 are typical wavelengths where we excite.
Okay. All right. Well, thank you very much, Sara. One thing to mention, Todd, is last year the Emeriti from Santa Cruz had a great response to this survey that System-Wide sends out, and that's coming up again in October?
Early October.
Before our next meeting. So they're going to send you all a survey saying, what are you doing, what are your activities, what are you contributing to the university? And we come out very well, we want to come out very well.